Hi, this is Steve Denenberg. In this video, we are going to work the first of the free response questions, that is the essay questions, from the AP Physics 1 examination in 2021. The College Board publishes the old tests for the essay questions, which they call the free response questions. They don't publish the multiple choice questions. It would be nice, but they don't. And looking at the old free response questions can be very helpful beyond just the practice of working problems like that, and I will show you how they can be very helpful. So let's take a look at the problem and do it. So here is the problem. A stunt cyclist builds a ramp that will allow him to coast down the ramp and jump over several parked cars, as shown above. To test the ramp, the cyclist starts from rest at the top of the ramp and then comes down, leaves the ramp, jumps over 6 cars, and lands on the second ramp. H sub naught is the vertical height of the cyclist when he starts. Theta sub naught is the angle at which he initiates his jump. X sub naught is the horizontal distance that he travels during the time that he's airborne. And it says down here, M sub naught is the combined mass of the cyclist and the bicycle. And they want to derive an expression for the distance, X sub naught, in terms of everything else. All right, so don't panic. Don't start throwing random equations at this thing. The first thing to do is to not write anything down and just figure out what's going on. So what is going to happen? Well, he's going to coast down the ramp. He's undoubtedly picking up speed as he comes down. So what's he doing? He's trading his height for speed. He's trading his gravitational potential energy for kinetic energy. And he goes down way down here, and then he launches at some angle theta. They mark it here, right? But that's going to be the same as this theta here. And then we know what's going to happen just from playing catch. He's going to go up in the air and come back down. And they want to know how far he traveled while he was up in the air. Well, what would you want to know? Seems you'd want to know how fast he's traveling when he launches over the cars, right? And seems you can figure that out because he starts with no kinetic energy up at the top, but he's got this potential energy. And when he gets down to here, he's lost that potential energy and he's turned it into kinetic energy. So we should be able to figure out how fast he's traveling. And then what happens after he launches? Well, he's going to take off at a certain angle, and you know he's going to have a horizontal component to his velocity and a vertical component to his velocity, and we do that all the time. And the horizontal component of the velocity is going to stay the same all the way across because gravity is going to be changing the vertical component of his velocity clearly because he starts out going up. When he gets to here, his vertical velocity is 0 because he's heading straight across. But that horizontal component won't ever change until he hits here. Well, can't we say that a distance that somebody goes equals his speed times the time he's doing it? That's one of the first equations we learned. Distance equals time times velocity. So we can figure out what his horizontal velocity is from determining that horizontal component when he launches. And we should be able to figure out how long he's in the air doing this. And then the distance that he travels will be that horizontal velocity times the time he's in the air. All right, well, let's start playing with that. Let's say that here's the horizontal, and he's going to launch in that direction with that angle theta, and let's call his speed v sub naught. We'll figure out later what it is from working the energy of his potential energy turning into kinetic. But so he's coming out at v sub naught, and he's going to have a vertical component of his velocity, and he's going to have a horizontal component of his velocity. And the horizontal component is going to be v sub naught cosine theta, and the vertical component will be v sub naught sine theta. Now, are you going to get those two confused? Are you going to put the sine and the cosine in the wrong place? Let me show you how I do it, because here's how I do it every single time I get a problem like this. Yes, still, if we have a problem like this where there's a certain theta and I know one of them is going to be cosine and one of them is going to be sine, what I do is I picture that the angle is actually very small. So here's our theta, and here's our v sub naught. Okay, so here's the vertical component, kind of, and here's our horizontal component. Well, if theta were super duper small like this, it's real obvious that this horizontal component is v sub naught cosine theta, because the cosine of a tiny, tiny angle is pretty much 1. If you look at the unit circle, remember that if you have an angle that's just teeny tiny, that the cosine of that angle is just about 1. So v sub naught cosine theta is going to be just about v sub naught, and we know that if this is v sub naught sine theta, that's going to be super tiny. So picturing a tiny angle helps me be secure that I know which one is the cosine and which one is the sine. So this is correct. All right, so we know now that the horizontal component is v sub naught cosine theta, and the distance he's going to travel, x sub naught, is going to be that horizontal component times the amount of time that he was in the air. And we are yet to figure that out. All right, so let's see what the vertical component is. The vertical component of his speed is v sub naught sine theta. And what is going to happen to his vertical speed as he completes his jump? Well, what does gravity do? Gravity provides a downward acceleration. And gravity is going to eat away at his vertical velocity, and then it's going to start developing a negative vertical velocity for him if we consider that the velocity is positive in the upward direction. So if someone starts with the vertical velocity of, say, 40 meters per second, and gravity is 10 meters per second squared in the negative direction, well, after 1 second, he'll only be going 30 meters per second, and after 2 seconds, he'll only be going 20 meters per second, and after 3 seconds, he'll only be going 10 meters per second, and after 4 seconds, his vertical velocity will be 0, and he will have gotten to this point right here, where he has no vertical velocity. And then the vertical velocity is going to start to get negative, because gravity inexorably is going to be adding to the negative component of his vertical velocity. So if he starts out with a vertical velocity of, what was it, v sub naught sine theta, and we wait t seconds, gravity is going to decrease his vertical velocity by t times g meters per second. His vertical velocity is going to be v sub naught sine theta minus t times g. And that's right from a formula that's on our formulas page. In fact, let's go find it. In fact, it's the very first equation on the page. They're talking here about velocity in the x direction. And what they say is the velocity is your initial velocity plus your acceleration times the time. How fast you are going is your initial speed plus any tick-tock change in your speed based on your acceleration. So all we have to do is change those x's to y's, and we say the velocity in the y direction is your initial velocity in the y direction plus your acceleration in the y direction times how long you've been accelerating. Let's say your velocity in the y direction equals your initial velocity in the y direction plus your acceleration in the y direction times how long you've been doing it. This is a very basic equation, and you should understand this thoroughly. Your velocity changes based on how long you've been accelerating. Okay, so your velocity in the y direction equals your initial velocity, which is v sub naught sine theta, plus your acceleration times time. Your acceleration is negative g times time, because plus is in the upward direction, this is in the upward direction, and as the clock ticks, you're going to be slowing in your upward ascent and then increasing your downward ascent. So let's figure out how long it takes for you to get from your launch point to the spot where your velocity is 0. Okay, that's when this is 0. When your vertical velocity is 0, the right side of that equation will hold. Okay, so let's say v sub naught sine theta minus gt equals 0. We'll say v sub naught sine theta equals gt. And then, so we're trying to find time. So v sub naught sine theta divided by g equals the time. And this is how long it's going to take you to get here, to get to the peak of your arc across those cars. So how long will it take you to get all the way across? Well, however long it takes you to get here, it's going to take you the same amount of time to get back down to here. This nice curve from the constant pull of gravity is going to be duplicated on the other side. So now I think we're getting close, because I think we know this t is to get you to the top of the arc. So to get you all the way to landing again is 2 times that. So 2 v sub naught sine theta over g equals your time in flight. Okay, and didn't we say that distance equals velocity times time? Well, so your horizontal distance is going to be your horizontal velocity times how long you were in the air. So we're about to find this, and that's their x sub naught. That's the time you're in flight times the horizontal velocity. Now the horizontal velocity is v sub naught cosine theta. That's your horizontal velocity. Here's your total time in flight to get to the top and then back down to the ramp. So that's times 2 v sub naught sine theta over g. And that's x sub naught. So let's write it out a little prettier. That would be 2v squared cosine theta sine theta all over g. So that's x sub naught. But we still haven't figured out what v sub naught is. Remember that? V sub naught is what we said. He comes down the ramp and he comes up and he launches right here at the theta. Now they tried to fool you by putting theta right here, but they couldn't fool you that way. But so we said that's v sub naught, but let's figure out what it is now. So we're going to do what I always say to do and what you heard me say to do a number of times in the energy and work chapter. We start out with energy initial equals energy final. His initial position here and his final position is where he launches into the air. This is where we want to find out his speed. There's no friction. He's just trading potential energy for kinetic energy. So then we say potential energy plus kinetic energy initial equals potential energy plus kinetic energy final. He starts with this, which is mgh sub naught, potential, and no kinetic energy. Right when he launches, he's lost his potential energy, and his kinetic energy is 1/2 m v sub naught squared. And I put the m sub naughts in there because that's what they said, even though his mass isn't changing. So let's grab this and go back down where we're doing our work and continue on. I'll rewrite it. M sub naught gh sub naught equals 1/2 m sub naught v sub naught squared. The m sub naughts cancel out. We'll multiply both sides by 2. 2g h sub naught equals v sub naught squared, and v sub naught equals the square root of 2g h sub naught. This is not hard stuff, folks. We started out with some potential energy. We came down, we turned it into kinetic energy. We figured out the vertical and horizontal components of his velocity. We saw how gravity ate that away, and that the horizontal velocity was constant. The vertical velocity being attacked by gravity gave us his time in flight. And then you just multiply that by the horizontal velocity to get your x sub naught. So let's go back down. So here's our v sub naught. And our x sub naught, we have to plug our v sub naught in there. So let's do that. X sub naught equals 2 times v sub naught squared. Okay, we didn't even have to take the square root. 2 times 2g h sub naught times cosine theta times sine theta all over g. Now, we can simplify this. The g's are going to cancel out, and we'll say x sub naught equals 4 h sub naught cosine theta sine theta. Done. That's their answer. So what did we do once again? All we did is we sat and looked at it. We tried to figure out what was going to happen. And once we knew what was going to happen, it was kind of obvious what equations to use. So let's go on to the next part of this very problem. Here's part B of the same problem. If the vertical distance between the top of the first ramp and the launch point were 2 h sub naught instead of h sub naught, with no other changes, what is the maximum number of cars the stunt cyclist could jump over? Justify your answer using the expression you derived in part A. Okay, let's go back up here. So what they're saying is, if we double the height at which he starts, we're doubling the height from where he starts down to the launch point, what's going to happen to the horizontal distance that he travels? With h sub naught, he could jump 6 cars, because that's what x sub naught turned out to be. So what happens to his distance when we double h sub naught? Well, I hope that's going to be easy, because the horizontal distance that he travels is directly proportional to h sub naught. So let's say x sub naught using 2h sub naught is going to be 4 times 2h sub naught times cosine theta times sine theta. And the original x sub naught using h sub naught was 4 h sub naught cosine theta sine theta. So if we double the height, we're going to double the horizontal distance, because this is the horizontal distance. So if he jumped over 6 cars before, he'll jump over 12 cars this time. But read the problem. It says, what is the maximum number of cars a stunt cyclist could jump over? That's 12. Justify your answer using the expression you derived. So how do you justify it? You say exactly what we just said. You said, well, the equation that shows the horizontal distance is directly proportional to h sub naught. You can write it however you want. So if we double this, we double that. That's all you have to say. And there's a third part to this question, so let's take a look at that. On the axes below, sketch a graph of the vertical component of the stunt cyclist's velocity as a function of time, from immediately after he leaves the ramp when he launches to immediately before he lands on the second ramp after he's cleared the cars. So here's time, and here's the vertical component of his velocity. It says, on the vertical axis, clearly indicate the initial and final vertical velocity components. Take the positive direction to be upward. You know what I do sometimes? I read these problems aloud. Whisper them to yourself. Now you've already done the math, so we should be able to figure this out. Let's see. So we know that the vertical component of his velocity when he launches is v sub naught sine theta. But remember, we had to plug in what v sub naught was, because they didn't give that to us. And here it is right here. V sub naught is the square root of 2g h sub naught. So v sub naught equals the square root of 2g h sub naught. And the vertical component was v sub naught sine theta. And that's the square root of 2g h sub naught times sine theta. So they wanted us to plot the vertical component. So we start out positive, he's heading up, and let's put it right here. They didn't give us a scale, so we can put it wherever we want. I'll erase this so I can draw a nice label. And we'll say that this is square root of 2gh sub naught sine theta. Be careful not to put the sine theta underneath the radical sign. Now, so what happened to his velocity? His velocity started out with that vertical component, which we now know is the square root of 2gh sub naught times sine theta. And it went to 0 because the vertical velocity is decreasing constantly with gravity. And when he got down to here, what was it? It was negative square root of 2gh sub naught times sine theta. Now, besides the symmetry of the drawing, we know that his velocity here has to be v sub naught, just like his launch velocity was v sub naught, because nothing was done to steal energy away from him. He just traded kinetic for potential energy and then traded it back, because when he hit the ramp here, he was at the same height above the ground as he was here. And gravity decreased his vertical velocity steadily over the time that he was going. So on our chart, if we started out at the square root of 2gh sub naught sine theta, we're going to end up at negative the square root of 2gh sub naught times sine theta. And drawing a line between them, we would draw a straight line because the velocity changed steadily as he descended. If you want, we can even write it out. What'd we say? His velocity equals his initial velocity plus acceleration times time. Acceleration is negative g. So his velocity equals his initial velocity minus g times time. Now look at this. On this chart, check this out. The vertical axis is velocity, and the horizontal axis is time. So time is kind of our x, and the vertical velocity is our y. So if we say that y equals v sub naught minus g times x, let's rewrite that. Y equals negative g x plus v sub naught. To me, that looks like y equals mx plus b, which is a line, a straight line with a slope of m, so his slope is negative g. Our chart of y against x, which is vertical velocity against time, is the equation of a straight line. So that's further confirmation for us. And you could come up with this on your own. You just have to sit and think for a second. You already knew what the initial vertical velocity was, because you had to work that out to get the horizontal distance x sub naught. And when you looked at his arc, when he jumped, you would know that afterwards it's that. So that's the end of that problem, which a couple of YouTubers said was the hardest problem on that test. I hope you look at that problem and say, wait a minute, you sure there's not more to it? It really didn't look all that hard. Let's take a look at some other stuff that's available. Now, I will have links to these in the description, but all I did was to search for AP Physics 1 past exams, and here it is, collegeboard.org. And when you go there, you will find a page that lets you browse past year's exams. This shows 2021 and 2020. And I know it goes all the way back to 2016 for sure. So you click on one of those years, and you get a menu like this. This is for 2021. And if you click on free response questions, you get the questions, just like the one that we just answered. But some of the other information is completely fascinating. You can click on scoring guidelines, and those are the guidelines that are given to the scorers, what they're supposed to look for in order to give you partial credit or full credit for a problem. A couple of things that I learned in reading some of these, and I'll probably learn more, is that when they say, write a paragraph describing why X, Y, and Z, well, they want to see a paragraph. And if you can explain why X, Y, and Z in one quick sentence, you'll only get half credit. So don't get too verbose, but if they ask for a paragraph, give them 3 sentences. There's the chief reader report, which is very interesting to read. The chief reader goes through everything, and he comes up with stuff to complain about. So, for example, on this very problem, he said a lot of students didn't seem to really understand what gravity does to the vertical velocity component of an object. But it's all that equation, v equals v sub naught minus gt, which is the same as v sub naught plus at. A constant acceleration makes a constant change in your velocity. He complained that some students were able to get the answer, but when asked what would happen if h sub naught were doubled, they didn't know how to come up with the answer. So we'll be talking more about that in a future video, just to make sure you guys understand that. And then also very interesting were the sample responses. They show you Xeroxes of the pages that other students filled out. Students who got everything right, students who got some of it right, students who really messed it up completely. And they tell you how they were scored. And some of what you learned there is completely fascinating. For example, in part A, when asked to come up with an expression for x sub naught, a student got it wrong. But in part B, when asked what x sub naught would be if h sub naught were doubled, he doubled the wrong answer that he got in part A, and they gave him credit for it. Because in part B, they were asking him to make that comparison between h sub naught and 2h sub naught. He didn't have the right answer here, but he manipulated it correctly to double his x sub naught, and they gave him credit. On another student's grading page, the student got the v sub naught, the launch velocity, wrong. He probably didn't write down energy initial equals energy final, and maybe he didn't come up with this, or maybe he did, and he didn't manipulate it right to get to v sub naught like we did. He got it wrong, but he still got half credit, because the scorer could tell that he was striving to use energy to get to v sub naught. He didn't get there accurately, but the fact that he knew that he was supposed to use the potential energy changing into kinetic, and what he needed was this v sub naught so he could plot this, that got him half credit. So even if you're not sure what to do on a problem, work on it. Doodle on it. Write down what you know. All right, that's enough for right now. I plan to do a bunch more of these if I have time. and hopefully you'll get the feel for them. As always, thank you for your attention. Any suggestions to improve these talks would be appreciated. You may have noticed that I didn't spend hours preparing for this talk like I have for some of the previous ones, but I hope you got something out of it anyway. Thank you.